Great. So you're welcome to today's class. Hopefully you're paying attention wherever you are. Hopefully you're going to take note. And I want to just encourage you to please pay attention. Pause the video whenever you need to. Repeat the video whenever you need to. Make sure you're making the most out of this session. So we're going to go through today's lesson. We're going to quickly go back to last time and wrap up and try and finish whatever we're doing last time. We're going to do more on redox reactions. We're going to do something called single displacement reactions. We're going to go to describing redox reactions. Then we're going to go to I do, you do, we do. Yeah, we did this last week, so this is actually going to tie into this. Okay, so just so you know. So the new things we're going to be doing today is redox reactions. We're going to go further into redox reactions. We're going to go more into single displacement reaction. Then we're going to go into describing redox reaction. So that should be it for this lesson. Then we're going to do I do, we do. I'm going to give you like an exit ticket for you to try on your own in your notebook. Great, great, great. And don't forget our usual announcement is on Tuesdays and Thursdays we have office hours and we have tutorials. The time is 3 p.m. Arizona time. And I keep inviting you, nobody shows up, but yet you're struggling and you still keep it to yourself. The reason why I'm waiting for you in office hours so that we can have one-on-one interaction. So please don't sit at home and be struggling and still not show up. Okay, that doesn't help you. It doesn't help me too. So hopefully I see some people show up this week. And those who have been showing up though, thank you so much. So last time we ended on assigning oxidation number. How do you assign oxidation number? We said that to assign oxidation number, you needed to know 4 rules. These 4 rules or guidelines will help you. And we said those 4 guidelines, and last time we ended by trying to assign oxidation number for this particular question. So we had question A. The question was H2S, and we're supposed to assign the oxidation number to all the elements here. So we started with H. We said that the oxidation number for H is +1. That was according to the first guideline. Then now the next thing was to find the oxidation number for S, which we solved here. We said that since we know the oxidation number for H is +1, we're going to represent in this reaction there's 2 of H. So we have +1 and 2 multiplying the +1. We don't know the oxidation number for S, so we just represent that by any alphabet you want. So we use X here. So X plus 2 multiplied by the H, which is 2 multiplied by 1, equals 0. Now we equated it to 0 because there's no charge on H2S here. So when there's no charge, equate it to 0 according to the guidelines. So we have X, 2 times 1 is 2. So X plus 2 equals 0. Plus 2 moves to this side of the equation. We have X will be equal to -2. So therefore, our oxidation number or the oxidation state for sulfur, or the charge, if you want to call it charge of sulfur, if all of this was an ionic compound, will be -2 for sulfur in this particular compound. And that's our final answer. We won't continue from there. We're going to try SO3 raised to the power -2. Just so you know, let's go back so you remember what we said about the oxidation, the 4 rules. The first rule says that the oxidation number of an atom in its elemental state is going to be 0. When we just have an element in its raw elemental state, as on the periodic table, the oxidation number is 0. It has no charge. The second rule says that the oxidation number of a monoatomic ion is going to be equal to its ion's charge. If you have an atom if you have an ionic compound which is made up of just one atom, then the charge of that atom is going to be the oxidation number or the oxidation state. We said that for the third rule, it says that for Anytime you see hydrogen, the oxidation number is going to be +1, except if the hydrogen is being combined with other metals, then it's going to be -1. If it's not being combined with other metals, it's going to be +1. If you see oxygen, the oxidation number straight away is -2, except if oxygen is being represented as a peroxide. If you see oxygen in this state, then we're going to assume that the oxidation number is going to be -1. If oxygen is in superoxide state, means you see oxygen in this state, then straight away we know that the oxidation number is going to be -1/2. Keep that in mind. And oxidation state is going to be a positive value when it's combined with fluorine. Now we said that all halogens, if you don't know what halogens are all the elements that are in group 17 if you're looking at a big periodic table, or group 7 if you're looking at a condensed periodic table. All elements in that group, they are the elements that end with chlorine, fluorine, iodine, all the in. Those are halogens. And we're saying that all the halogens, the oxidation number is going to be straight away -1, except if oxygen is being combined with the halogen, or if the halogen is being combined by other halogens, then it's not going to be -1. It's going to have a positive oxidation number. Keep that in mind. Then the last rule says that the sum of oxidation numbers for all atoms in a molecule or a polyatomic ion equals the charge. So if you have a group of compounds and there's a charge on top of that compound, you're going to equate the sum of each individual oxidation number and equate it to that charge. That is the last rule. We're going to use these 4 rules to guide us anytime we are assigning an oxidation number. Please refer to these 4 rules. You're going to need them. I can just expand one here for you. All the metals in group 1, their charge is going to be +1. All the metals in group 2, their charge is going to be +2. It's just the same as what we hear for hydrogen +1. So keep that in mind. That is going to be useful. So we are back. We are back to what we are doing for this lesson. We're going to try and assign the oxidation number for SO3. This is sulfate ion. So let's try this together. So we have SO3 with sorry. Remember we spoke about 2 minus. We spoke about how to write the charge and how to write the oxidation number. If you remember last time, we said that the proper convention we said that when you're writing the charge, you write the number first, followed by the sign. So this is the correct way to write the charge. If you're writing the oxidation number, you write the sign, then followed by the number. Let's keep that in mind. So this is for charge. This is how to write the charge. And this is how to write, that's the charge. If you want to write the oxidation number, the sign comes first, followed by the number. So this is oxidation number, and this is charge. Just keep that in mind. Great. So we want to come back to where we were. Good. So we're going to try, and we're trying to write the oxidation number for each of the elements. So let's start with S. We don't know the oxidation number for S, so let's represent that with X. We're going to solve that. But for O, we know the oxidation number for O. Based on the guidelines we saw, one of the guidelines said that anytime you see oxygen, the oxidation number is going to be -2. So the oxidation number is -2. Remember, it's the sign followed by the number. That's the oxidation number. So now we know the oxidation number for oxygen, but we don't know that for sulfur. So let's find sulfur's oxidation number. To find sulfur's oxidation number, you're going to apply all the guidelines. It said that one of the guidelines said that you're going to equate each individual oxidation number to the charge of the compound. So the charge here is 2 minus or -2, right? So we're going to represent each each element's oxidation number, the sum of each element's oxidation number, and equate it to the charge. We don't know S's oxidation number, so let's write X because we say we're going to represent it by X. Plus, we're writing the sum of each of them. What's the oxidation number for oxygen? We said it's -2. So put -2 in a bracket. Now, how much of oxygen we have here? We have 3 of oxygen, so put 3 here. Now we're equating the sum of the oxidation number for each element. We equate it to its charge. The charge is -2. Great, now let's solve this. This is algebra. The rest is just simple algebra. So from algebra, x will be, now 2 times 3 is 6, but there's a negative, so -6. If you don't know what is happening here, 2 times 3 gives you -6. Anytime you have minus facing or coming into contact with plus, minus will always be more powerful than the plus. So we have x minus 6 equals -2. Do you see that? So now we're going to have x now be equal to this -2. If it crosses the equal to sign, it becomes positive. So we're going to have -2. The -6 crosses and becomes +6. So what we actually have is 6 minus 2. And our answer is 4. Or you can write +4. However you want to write it. Okay. So that means that our x is +4. Remember, x was just standing for the oxidation number for sulfur. So finally, the oxidation number for sulfur will now be equal to what? +4. And now we solve our question. Or you can write it here, +4. So oxygen was -2 and sulfur is +4. So then you're correct. You solved the question. So that is how we deal with assigning oxidation number or calculating oxidation number. Good job, good job. If you didn't get it, please rewind the video, just go back a little bit and watch this again. That'll help you. Okay, so what was the other question? The next question was to find find oxidation number for each of the elements. So we're going to have to find the oxidation number for each of the elements in that compound. So let's try that together. What was the compound? Na2SO4. So let's try it. We have Na2SO4. We have Na2SO4. So we want to find the oxidation number for each of the elements here. So let's start with Na2. We have Na. What's the oxidation number for Na? That's sodium. Sodium is in group 1. Sodium is in group 1. We're saying all the group 1 elements, we know their charge. So sodium, group 1 elements form a metal. All the metals in group 1, they have a charge of +1. And their charge is the same as the oxidation number. So it's going to be +1 for sodium here. What is the oxidation number for S? We don't know that. So let's represent it by X for now. We're going to solve that. The oxidation number for oxygen, we know that. We said that always oxidation number based on the guidelines or the rules. We said oxygen will always have the oxidation number of -2. So let's solve the oxidation number for S. The oxidation number for S, let's go. So we are solving for oxidation number for S. Based on our guideline number 4 or the rule 4. Rule 4 says that you're going to sum the individual oxidation numbers of the element and equate it to the charge. Now in this compound, as you can see, there's no charge. So the charge is 0. There's no charge written up here, 0. So we're going to sum the individual oxidation numbers of the element and equate it to 0 because that's the charge. There's no charge. So we're going to have Na. What is the Oxidation number for Na. We start with Na is here. Na is plus 1. So I have plus 1. But remember, there's 2 here. There's 2 of Na here. So we multiply this by 2. Bring your plus. We're summing it up. We have S. What's the oxidation number of X? We are representing it by X. So I put my X here. What is the oxidation number for oxygen? We said it's minus 2. So I have minus 2. I'm putting it into a bracket because there's a 4 here, and that 4 is going to affect my minus 2. So I put 4 here. And we said we are equating everything to what? 0. I hope you're following me. Please be doing this with me. Take your notebook. Follow me. That's the best way to understand it. Follow me. We are looking for the oxidation number for S. We don't know it, so we represented it by X. So that is it in here. So let's move on. We're trying to solve X. This is common algebra. 2 times positive 1 is going to be 2. We have our plus. We have X here. Sorry, I should have brought a plus here because it's the sum. We're doing the sum, right? I have X here. So let's move on. X. Now, minus 2 multiplied by 4 gives you minus 8. So we have minus 8 here. Remember, negative and positive, negative will always win. So we have minus 8 here equals 0. How do you want to go about this? We can go about it in so many ways. We did normal algebra. So let's do 2 plus x here. And let's move minus 8 to this side of the equation. We're going to have positive 8 like this. And the next thing you want to do is what? Now let's move this 2. It was positive. Move it to the outside of the equation. We're going to have x equals 8. This 2 was positive. If it crosses the equal to sign, it becomes negative 2. Our final answer, x, will now be equal to what? Plus 6. Because we said oxidation number, when you're writing oxidation number, the sign first before the number. So it means our oxidation number for S in this particular compound is going to be what? Plus 6. So now our answers are complete. Na is equal to plus 1. That's the oxidation number for sodium. For S, which is sulfur, we have plus 6. That's what we just solved. Now for oxygen, we have what? Minus 2. And that is your final answer. This is basic algebra. If you have problems with algebra, then it means you're going to have some problem here. And I apologize for that, but that is why I'm happy. I'm happy that this is I'm happy that this is I'm happy that this is a video. You can watch this video. You can watch this video. This is a video. So please, if you're having problem with algebra, take your time, watch this video and come back again. Watch it till you get this, okay? So if you don't have any questions, we can just move on to the next thing. So let's move on. So I think we answered all the 3 questions. Yeah, so we answered all the 3 questions. So we want to just move on. So the next thing we want to look at is more on redox reactions. So if you've been wondering, so far we've been looking at redox reactions. We've been saying that redox reaction is just basically It's just a combination of reduction reactions and oxidation reactions. Remember, we spoke about oxidation. We said general oxidation is when oxygen is combined or involved in the reaction, but we said redox reactions enlarges the understanding of oxidation and reduction. Okay, it gives it even a larger explanation. It says that when you're losing an electron, that's oxidation. When you're gaining an electron, that's reduction. And this principle governs a lot of different processes that happens. One of the core parts of this redox reactions is what we call combustion, right? And last time we discussed combustion. One of the big applications of redox reactions, which is combustion, is what you're seeing here. What do you think this is? Anybody? Yeah, as you can see, this is a rocket. It is a rocket that is being launched, or that has been launched, and it's crossing the atmosphere, the stratosphere, all the spheres that you can call is going into outer space. Now, solid rocket fuel reaction. So most of these rockets, for the rockets to be launched, we need a lot of energy to be generated. Now, the energy to be generated needs a lot of heat, needs a lot of burning of fuels. Most of these fuels are made based on the understanding of redox reactions, specifically combustion, right? So we're saying that the solid rocket fuel, so some of these fuels are made from solids, and these solids are just applying the concept of combustion, which in essence is just reduction and oxidation, where we have a reductant. Most of the time in a combustion reaction, we said that there's a fuel, right? And there's oxygen. I don't know if you remember. We spoke about this at the beginning of our class. So most of the time, the fuel is actually a reducing agent. Most of the time, the fuel is actually a reducing agent. A reducing agent. A reducing agent or a reductant. Reductant is the same as a reducing agent. So look at this particular reaction we have down here. So look down here. This reaction you see down here, that's an example of what we are talking about. So look at this reaction down here. You see, so you see we have this reaction. Actually, this reaction is an example of the type of a reaction that is going on. Propellant, it's called a propellant reaction. Look at it. Propellant reaction. Now looking at the word propellant, what do you think propellant is? Propellant, to propel something is to create a forward movement, to propel something. So most of these rockets are propelled by a reaction. The reaction is supposed to be a very great reaction, generating a lot of heat energy with force that pushes the rocket up. And we are saying that an example of a propellant reaction is shown above here. And in this reaction, we see solid aluminum is being oxidized. Okay, so they generate a reaction by having aluminum. And you see there are 10 of aluminum. So there's a large amount of aluminum, 10 aluminum, and there's 6 of ammonium perchlorate. So we have our oxygen term here to help oxidize aluminum. So the oxygen here is just supposed to help cause a reaction here with aluminum. So our reducing agent or the fuel here, we see aluminum here acting as the reducing agent here. And so we're going to have a big reaction here, a propellant reaction. That's the type of reaction. So this just to give you an idea to know that, okay, all we are studying, it's really applicable to the real world. And this is an example of some of the reactions going on. So the fuel from that propels some of these big rockets to launch into space and all the exciting expeditions. Behind all this is just basic understanding of redox reactions, where we have combustion process, which is basically a fuel and oxygen. And we're saying most of the time the fuel is a reducing agent. If you don't remember what we said about reducing agent, we said that when we have, for example, we have sodium becoming sodium in a half reaction, sodium becoming NaCl. We're saying that sodium is undergoing what? Sodium is undergoing oxidation, where sodium loses electrons. So here, sodium was Na plus. I'm just reminding you of what we learned already, Na plus. It lost an electron to become Na plus to combine with Cl here. Okay, it's something similar here. It's the same thing happening to aluminium. If you look down here, aluminium was just a solid, but aluminium goes through oxidation where it loses electrons here. How I know it loses electron because it combined with oxygen here. It underwent oxidation. That's what we're talking about. So you see, the basic thing we learned is what is being applied by scientists here, and they use this to generate a lot of energy to cause a rocket to launch. Okay, so that's how the basic knowledge we're learning here is the same thing being applied. That's the whole import of what I'm trying to show you in this particular slide. So know that the basic concept you're learning is being applied in a larger scale. Okay, that is just to get you excited to know that, okay, so what I'm learning, I can apply in a big scale to do big things, right? Great, 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 great. Excellent. And so just a quick one. So sodium is undergoing oxidation, and we're saying that when sodium is oxidized here, sodium is undergoing oxidation. This is also called what? The reducing agent. Okay. So in just this simple example, sodium is also called a reducing agent. It's the same thing for aluminium down here. And the aluminium undergoes oxidation, but the same aluminium will be the reducing agent, or what we call the reductant. Okay, so most fuels are the reducing agent or the reductant. So think about all the fuels you can think about. So in these big rockets, they find substances or elements that will undergo oxidation, and those elements become the reducing agent. So we need elements that we know will undergo oxidation, and they use them in these reactions, and they generate a lot of energy to propel the rockets. Yeah, so great, great. I hope you learned something great from this slide. I want to move on. So this video is for you. I want you to. I'm going to attach this slide to Canvas. When you go into Canvas, you should be able to open the slide. I want you to click on this video, and this video is just an illustration of. It's just an illustration of um. Just an illustration. It just gives you an example of what we're talking about rockets being launched and how oxidation and reduction is applied. Okay, and I would like you to go watch this video just to give you more understanding in what we're talking about. In the video, you're going to see that some of the engines, based on the kind of reaction that is being generated, some of the engines release more fuel or release more energy than the others. Okay, so based on specific reactions, so for example, some of the fuels, we are saying that when the fuel is a liquid fuel, look here, when there's a liquid fuel, it's more powerful compared to it. So the first engines firing at 3 seconds used a liquid fuel. So when we have a fuel which is a liquid fuel, it's less powerful. When we have the fuel to be a solid fuel, it's more powerful. So it's just like what we were looking in the initial slide. Remember, the reducing agent or the reductants act as the fuel. So they're saying here that from a video that you're going to watch, you realize that when the reducing agent or the reductant is a liquid, it generates energy, but the energy is less compared to when we have a solid fuel. And I want you to think about it. Why do you think the liquid fuel compared to the solid fuel, one generates more energy than the other? I want you to think about this. Go do a research on this. I'm going to ask you this question. Yeah, I'm going to make sure I can bring it in an exam. That'll be a fun exam question. Let me write it down somewhere. Let me write it in this slide so that I don't forget. Exam question. And the question is why um solid fuel versus liquid fuel versus liquid fuel in rockets, in rockets engines. That'll be a good exam question. Great. So make sure you try and watch this video, think about it, and think about this question. You might see it in an exam, and I hope you enjoy it when you see it in an exam. If I were you, I'll go read about it. Okay. Great, great, great. So we want to move on. Great. So this will be something I need you to pause and think about it. Find an answer for this right now. Write the explanation you find in your notebook. When we come to class the next time, remind me about it, share it with the class. Let's learn together. Great, great, great. So let's move on. Let's move on. So we want to go move to the next thing. We're looking at single displacement or what we call replacement reactions. Single displacement or what we call replacement reaction. So one of the first things you want to take note is that this type of reactions, they are an example of a redox reaction, which we're trying to look at. They're an example of a redox reaction. So an example of a redox reaction is a single displacement reaction. What is the meaning of single? It's just a big word, single displacement or single replacement reaction. That's a fancy word. What does this word actually mean? We're trying to look at what does this mean. From the meaning or from the word, first of all, single. Single means one. So think about it. Most of the time, the words carry the meaning. Okay. So single means the action is just singular, one. The next word is replacement. It means that something is being replaced by another thing. Okay. So these two words to give you a clue about what you're talking about. So one is a type of redox reaction. That's the first thing. The second thing, we're saying that in this type of redox reaction, an ion in solution is being displaced or is being replaced by a metal. So an ion in solution. So in solution means that aqueous. It means that whatever ion has come out of its compound because it's dissolved in a solution. So we have a compound or a salt. When we dissolve the compound in solution form or in liquid or in water, the ions, the individual ions broke apart. That's what we're saying, right? So the individual ions broke apart, and we're saying that when the individual ions broke apart, one ion is replaced by a metal, and that kind of reaction is called a displacement, single displacement reaction, or a single replacement reaction. Okay, so think about this. Anytime you're looking at a single displacement reaction or a single replacement reaction, one of the things we want to think about is that there should be a metallic element replacing an ion. Okay, so in a single displacement reaction, it should be a redox reaction. One. Number two, we're saying that an ion is being replaced by a metal. So we see a metal in the reactants, and in the product side, we see that the metal has combined with another element and replaced an ion. So let's carefully look at this example here. We have, first of all, can you identify the metal? That's my first question for you. Look at this reaction. Can you identify the metal? Everyone, pay attention. Which of them is the metal? If you say chlorine is the metal, I don't agree with you. Chlorine is not a metal. Chlorine is not a metal. If you say hydrogen, I don't agree with you. Hydrogen is not a metal. Chlorine is a halogen. Hydrogen is a gas. So hydrogen is a metal in a sense of a group 1 element, but it's the only exception in group 1. Most group 1 and group 2 elements are metals. The exception is hydrogen. Hydrogen is gas actually. So our metal is zinc. If you know zinc, that's the chemical element for zinc. Zinc is a metal. So we're seeing the features. We said that the metallic element is going to replace an ion. So look at this. We see, first of all, we know it's a redox reaction because look here. Most of the time in a redox reaction, we're saying that it involves losing of electrons and gaining electron. And one of the key things is that the oxidation number of one element, if you trace it, you're going to realize that it's going to change. Okay. So for example, look at zinc. Zinc doesn't have any charge here. So let's say zinc is 0 on this side. But when you trace zinc, we're going to trace zinc. Zinc didn't have any charge here. When you look at zinc here, now zinc is combining with chlorine. The only way zinc could combine with chlorine is that zinc assumed a charge. Okay. So here we see that zinc is now assuming a charge. What happened here is that zinc became +2 and chlorine was -1. And now to form a compound, it became zinc chloride. And that's what you have there. So it means that zinc was just zinc. Then now the oxidation number has changed. Zinc is now zinc +2. Okay. So this is a redox reaction. So we're saying that in this particular type of redox reaction, what is going to happen is that zinc, which is the metallic element, is going to replace an ion. So look at this carefully. In this compound, we could see that the ion was hydrogen. We had hydrogen plus and chlorine minus. The ion here was hydrogen. Now look at this side. Look at this side of the equation. You're going to see that now hydrogen is no longer here. In place of hydrogen, what do you see? Zinc. Zinc has taken the place of hydrogen. So this is a perfect example of a single displacement reaction where our hydrogen, which was combined with chlorine here, has now been replaced with zinc, which is the metallic element, and now it's releasing a gas called H2, hydrogen gas. It liberates the gas. So in this particular reaction, what is going to happen is that hydrogen is going to be produced. So this is one of the reactions that produces a gas. So if you have zinc metal and you put zinc metal in hydrochloric acid, this is hydrochloric acid. When you put zinc metal and hydrochloric acid, what you're going to generate, you're going to generate zinc chloride, and hydrogen gas is going to start coming out of that reaction. So this is one of the ways of producing hydrogen gas. When you put zinc in the aqueous solution of hydrochloric acid, we're going to generate hydrogen gas. That's a perfect example of a single displacement reaction. I hope that makes sense. Great, 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 great. And we're saying that in another sense, one example or another example of a single displacement or replacement reaction is that in a single displacement or replacement reaction, we're saying that one of the examples is that a metallic element may also be oxidized by solutions of other metal salts. So the first type is what we just saw here. where a metal replaces an ion. Now we are saying that in the second type, a metal replaces another metal. So that's the second type. The first type was just a metal replacing any different ion in aqueous solution. This time we are going to see one metal replacing another metal. So an example is what we see here. This is the example. Now before we even go into the chemistry behind this example, let's just try and identify the metals, because the example is saying that two metals, one metal is going to replace the other, okay? One metal is going to replace the other. So let's see which metals are replacing which metals. First metal we can see here is copper. Let me change the color. So let's identify the metals. One of the metals is copper. Copper is a metal. The next metal we can identify is what is silver. If you don't know Ag, Ag stands for silver. Ag stands for silver. Right. So we are thinking about silver, but this silver is not solid silver. We're saying this silver is in aqueous form. So we have an aqueous solution. Silver is in a solution form. This is copper and it's solid copper. And this is silver nitrate. So look at this picture here. That's what you're seeing here. So we have a copper. So this is a solid copper. This is copper in its elemental form. Now we have in this in this test tube, we have silver nitrate. So inside this test tube, we have a solution. In that solution, we have a metal, silver, reacted with nitrate, and it forms this solution. We're saying that another kind of single displacement reaction is when a metallic element is oxidized by another solution of other metals. So this solution has a metal, right? And in this solution having a metal, we're going to see a loss of electrons and gaining of electrons going on in this reaction. But the difference between this number one and number two is that number one was just a metal replacing any ion. In number two, we're going to see a metal replacing another metal. So let's see how that happens. Before we go into the chemistry, once again, I want you to look at these pictures. So in this picture, what do you see? Anybody? What do you see? I see copper ion. So I see a copper. So this is copper metal. And I see this test tube with a liquid inside there. We're saying this liquid is is silver nitrate. So this silver nitrate is what is inside here. Okay. And copper is this. That's copper. We are saying that when we put this copper inside this reaction, when we put this copper inside this solution, something begins. So when I put when I put when I put this copper inside this solution, a reaction begins, right? Now, that reaction inside here is a type of redox reaction, which we're talking about here. It's a single displacement reaction. Look at this copper. The copper was brown, nicely looking here. When I put it in this reaction, something begins to happen to the copper. Now, something happens to the copper, a reaction is going on. So the chemistry behind what is going on here is what we're discussing. But the physical changes that you can see to depict what is happening chemically is that at the end of the day, you see that our liquid is now having a coloration. What is the color? We see a blue color. You're going to know why you're seeing a blue color. We also see that something is happening to the metal. The metal is it's shedding off certain particles. There's certain particles having a certain color which is not blue. It's shedding off the particles. Do you see that? Great. So there are two things happening there. We're going to explain all of that. Okay. So now in this reaction, you see, so all the things we're learning, they're so chemical, it's chemistry, but there's also physical changes happening. So we said that here, what is going to happen? We say one metal is going to replace another. So look carefully. What do you see here? Copper was here. It had no charge. So copper was here. It had no charge. Now let's follow copper carefully. Let's see what is happening to copper here. Let me change the color and use a different color. Now we see copper. Look at copper here. Copper was just existing as copper with no charge. This time copper is here, but copper is combining with nitrate. The only way that can be possible is that the oxidation state for copper changed. So copper was just copper as a solid. If you look at the half reaction, you realize that now had to become Cu, copper had to become Cu plus 2, right? To react with nitrate, NO3 minus 1. And that's how they form CuNO3 with a bracket. So I'm just trying to explain what is happening in here. So the oxidation number for copper here changed. Now copper displaced silver. Silver is supposed to be with nitrate, but you can see that silver is no longer with nitrate. Look here. Silver was combined with nitrate. Copper came, displaced silver, and now copper is sitting in place of silver. Copper changed its oxidation. So now copper was just Cu, it became Cu2 plus here. Okay, and so that's what we're saying here. One metal undergoes oxidation in solution and replaces another metal, and that is a single displacement reaction. Now you see what is happening here. Now we have copper nitrate in aqueous solution. So this liquid is different from this liquid. This liquid was silver nitrate. But when we put the copper inside here, a reaction began. Now the reaction results in a new liquid. Now this liquid is copper nitrate. The blue color you're seeing is as a result of the copper ions. So the copper ions reacting or undergoing oxidation and now being reacting with the nitrate gives you the blue color. So the blue color here is because of the Cu, the copper ions, Cu2 plus. Okay, the ions from the copper is what is actually going on here. The ions from the copper is what results in the ions from the copper is what results in what you see in the blue color, right? Now the second thing you see, we see we see Ag is silver. So the silver in solid, S stands for solid. So these particles you're seeing inside here, all these dots, these things you're seeing there, is actually the Ag, is this Ag. The solid particles are silver. Okay, the silver is shedding off, or the reaction is producing precipitates. We call that precipitates of silver. It's just particles of the silver. Okay, and that is what you're seeing there. So the silver is forming on the metal, that metal of the copper. Okay, the reaction results in silver solids. So this solid stands for silver. Okay, so this is an example of a redox reaction which we call single displacement or replacement reaction. Two things you want to remember. Number one, a metal replaces an ion. It can be any ordinary ion. The second kind is that a metal replaces another metal. So copper replaces silver in this particular instance. Okay, great, great, great. I hope this makes some sense to you. If it doesn't, please just go back a little, watch the video again, think about it, and write something down. Great. I hope you're learning something. So I want to move on. I want to move on. So I want to move on. Let's move on. Great. So the next thing we want to talk about is we want to talk about describing redox reaction. So we've been talking about redox reaction so far. We want to go further and describe. We want to be able to identify equations that represent redox reactions. Okay, so we're going to have to be able to look at reactions and be able to identify, okay, this is a redox reaction. If it's a redox reaction, then we need to know which one is the oxidant, which one is the reductant. What that means is that which one is the oxidizing agent, which one is the reducing agent, which we spoke about from the beginning. We spoke about how one substance undergoes oxidation, the other substance undergoes reaction. And the substance that undergoes oxidation becomes the reducing agent, and the substance that undergoes reduction becomes the oxidation agent. Don't forget that. Remember, that's what we spoke about last week. We're going to go further. So we're going to try and go through each of these reactions carefully. Try and understand what is going on here. Classify which ones are going to be redox reactions, which ones are not going to be redox reactions. And that's going to help us to understand more about redox reactions. So I hope you're ready. So just I'm going to give you some time. Try and look at it carefully. What is going on here? Try and see if you can identify anything here that makes sense. If you see Zn is zinc. CO3 is carbonate. This is zinc. This is oxide. CO2 is just carbon dioxide. You already know that. Ga. What do you think Ga is? Take your periodic table right now. Which element is Ga? I'm not going to tell you. Br. Which element is Br? Take your periodic table right now. Look at it. They form something called GABr. I'm not going to tell you. I want you to look at it yourself. We have H, hydrogen. We have oxygen. They form something here. We have H2O. That's water. That's oxygen here. Ba. Which element is Ba? I want you to take your periodic table. Look at it. Cl, chlorine. K2SO4. So this is potassium sulfate. We have BaSO4, barium sulfate. I just told you that. So try and look at these. Make sure you familiarize yourself with it. Most people get scared about chemistry when they see an element and they're like, this is strange. What element is this? What is the name of this element? Once they don't know the element, they just start closing their mind and they don't even want to think about it. Well, to do chemistry, you need to be brave, okay? Don't be scared about the element. When you see the element, be brave. Ask yourself, which element is this? Okay? Which element is this? Okay? Then you try and confront it. So are you ready? We're going to go through this together. I hope you're ready. Yeah, I am ready. I hope you're ready too. So let's look at this together. We're going to start with our first one. Our first one is, that was our first one here. We have our first one. So we want to look at this. First question is, let's look at what's the question. We want to identify which equations represent redox reaction. So that's the first thing we want to do. We want to provide a name for the kind of reaction we think it is. Then we want to identify if it's a redox reaction, what is the oxidant, what is the reductant. So I hope you're ready. So we want to start with this. This is our first one. I'm going to throw this question to you. What do you think? Is this a redox reaction or not? If you say it's a redox reaction, you need to be able to explain why is it a redox reaction. Is it a redox reaction? If yes, how is it a redox reaction? How is it a redox reaction? How is it a redox reaction? Anybody wants to help us? So anybody? Okay, let's look at it together. How do we tell if something's a redox reaction? We said that in redox reaction, there's reducing There's reduction and there's oxidation. Basically, what is happening is that one element is losing electrons, the other element is gaining the electron. And so once one is losing and one is gaining, their oxidation state is going to change, or the oxidation number or oxidation state is going to change, or oxidation state changes. Okay, that's how you know if it's a redox reaction or not. If you're confused about oxidation and oxidation state, we're just trying to say that there's something going on that affects their electrons. So one person losing an electron means it has a positive charge. The other person gains an electron, it becomes a negative charge. So the oxidation number is changing, and that is how you know it's a redox reaction. So let's look carefully at this. Okay, let's look carefully at this. So look at zinc. In this reaction, we see zinc carbonate. This is zinc carbonate. Zinc carbonate means that before zinc formed zinc carbonate, it was zinc and it was carbonate, CO3. This is how they were. These are the separate entities. For them to be one compound, they had to undergo a reaction. Okay, so zinc. Now, if you don't know um, the charge for zinc, let's think about carbonate. Carbonate. What's the charge for carbonate? Anybody? So CO3 has a charge of -2. So this CO3, it has a charge of 2 minus. Okay, it has a charge of 2 minus. Now, the only way they existed together is that zinc also has a charge of 2 plus. So for them to form zinc carbonate, zinc was here, zinc and zinc took the 2 from the carbonate. So you put that 2 here. Now carbonate also took the 2 from zinc. So you put the 2 here. So it's supposed to be this way. This is how they're supposed to look. But the 2's cancel out. So then we end up with zinc carbonate. Okay. So they exchange their charges because the charges are the same. They just cancel out. Then at the end of the day, we have zinc carbonate. So that's how zinc was formed. It means that zinc existence with a charge of +2. Okay. Look at this side of the equation. What do you see here about zinc? Look, zinc is still zinc reacting with something else called oxygen. What is happening here is that before they came together, it was still zinc +2 and it was oxygen -2. We're going to have zinc taking the -2 of oxygen is just 2. Oxygen taking that of zinc is just 2. The 2 cancel out. At the end of the day, we have zinc oxide. So as you can see, zinc is not changing its oxidation number. It's still the same. Likewise, oxygen. Oxygen is not changing its oxidation number. Okay. What is happening is that none of these are changing the oxidation number. They were all a solid. They are still solid here. And this forms a gas. We don't see anything like aqueous. There's no aqueous. Anytime we see aqueous, it means there's something dissolving in solution. And the dissolving in solution is actually resulting in someone losing an electron, somebody gaining an electron. So we just looked at zinc. If you look at zinc carefully, zinc did not change its oxidation. It's still +2. It's still +2. Okay, if you're still not convinced, let's look at carbon. Carbon, carbon. Let's see if we can find what was the oxidation number for carbon in this reaction. I want to clean and just look at carbon for you. We're trying to find if anybody change the oxidation number? Remember, we said that in a redox reaction, the oxidation number is going to change. That's what we're saying, okay? So we just looked at zinc. Zinc didn't change its oxidation number. Zinc was +2. Zinc is still +2, so zinc didn't change. Let's look at carbon. The oxidation number for carbon, if you want to find oxidation number, we already know how to find oxidation number. Okay, we are equating everything to the charge. So let's say the charge here is 0. Oh no. So I'm trying to find the oxidation number for C. Okay, I'm trying to find the oxidation number for C. C, look at C on the left side. C. So I don't know the oxidation number for C. Let's say I put X. Let's solve for oxidation number for C. We already know that the zinc is +2. So oxidation number for zinc is, we said is +2, right? So I have +2, then plus C. I don't know C, so let me put X. Oxygen, we know that it's is -2. Oxygen, the oxidation number for oxygen is -2. So I have plus here, then I put a bracket. There's 3 of oxygen, so -2 multiplied by 3. There's no charge, so we put 0. We're trying to find the oxidation number for C. I'm going to have 2 plus X. 2 times 3 is 6. I have -6 here, which is equal to 0. This is all algebra. I'm going to have 2 plus X. This 6 moves to the other side. I'm going to have +6. This 2 moves to the other side. I'm going to have X equals 6 minus 2 and X, which gives me what? 4. So the oxidation number for C is 4. Do you see that? Now let's come to C. Look at this here. We have C, the oxidation number is 4. Let's come to this side. Let's find the oxidation number for C here to see if anything changed. Okay, the oxidation number for C. I don't know oxidation number for C. I'm going to let's represent C by X. Oxygen. We said the oxidation number is -2. Okay, so let's look at that. So X plus what? I have -2 for oxygen, but there's 2 of oxygen, so I put 2. What's the charge? The total charge is 0, so I put 0 here. We're trying to solve for the charge of the oxidation number for C. So let's continue. I'm going to have X. 2 times 2 is what? -4 equals 0. Do you see what is happening here? X becomes equal to what? 4. So still the oxidation number for C is what? 4. So as you can see, the oxidation number for zinc doesn't change. The oxidation number for C doesn't change. Now the oxidation number for oxygen too doesn't change. How do I know that? Oxygen is still oxygen here. It's still -2 here. Oxygen is still -2 here because zinc is +2. The +2 of zinc and the -2 of oxygen cancel out here. In this compound, oxygen is still -2. So we can confirm here. No, the oxidation number doesn't change. So what is the conclusion? This one is not a redox reaction. It's not a redox reaction. How do I know that? There's no change in the oxidation number for the element. The oxidation numbers do not change for all the elements. That's how we know it's a redox reaction. Please don't forget. So A is not a redox reaction. If you were going to say it was a redox reaction, you'll be wrong. It's not a redox reaction. So let's go to B. So anybody who wants to take a guess, is B going to be a redox reaction or not? By now you've realized that there's no shortcut. We always have to go back to the basic rules we learned and start from the scratch. There's no magic to say that. And by now I guess you've realized that you can't just, if you're going to make assumptions and just guess, that's not chemistry. In chemistry, we're following certain rules, certain principles, and the principles are guiding us to make our decisions. Okay, so that's great. So first of all, I ask you to find a name. Who knows the name of this element? Anybody? What is the name of this element? That's where we want to start from. What is the name of this element? Anybody? What is the name of this element? Anybody? Well, look on your periodic table, you're going to see a name like this. Gallium. If you see this, that's the name. Gallium, gallium, gallium. I don't know how you want to pronounce it, but that's the name of that element. Gallium, gallium. That's the name of that element. Now, who knows the name of this element? This is an element called bromine. Bromine, or bromine, or I don't know how you want to call it. Okay, bromine. So we want to ask ourselves, is this an redox reaction? How do I tell? We're saying that if it's a redox reaction, the oxidation number of one or any of the elements will not remain the same. Okay, okay. So let's see if we can know if any oxidation number changes. Now I'm going to start with bromine. I'm going to start with bromine. Okay. So let's look here. Bromine. First of all, I know bromine is a halogen. Okay. So keep that in mind. It's going to be useful soon. Bromine here, we see bromine as just bromine sitting here, right? Now, when you look at bromine at this side, bromine has combined with the element gallium. The only way bromine was able to combine with gallium is that bromine has to exist as an ion. And so we have gallium and we have bromine. It means that gallium had to have a charge of +3, and bromine had to have a charge of -1, right? So that's what is happening here. That's the only way they could have combined to form Ga. This gives it 1 to this guy. This guy gives it +3 to this gentleman here. Then we have gallium Br3. Okay. So what this means is that now look here. Gallium was just existing with 0 here. This guy was also existing here. So this was just existing as 0 here. This was also existing as 0. As you can see, there was no charges on them. But all of a sudden here we have now gallium was existing with a charge of +3. This was existing with a charge of -1. So their oxidation number changes. So our first thing is that we know that this is a redox reaction. So this is a redox reaction. So this reaction is a redox reaction. Okay, great. Okay, so we know it's a redox reaction. Remember, what was the question? The question said that identify if it's a redox. If you identify now, we know that's a redox reaction. Now tell us which one is the oxidant or the oxidizing agent. Which one is the reductant or reducing agent? To be able to tell which one is the oxidizing agent or which one is the oxidizing agent and which one is a reducing agent. You need to know what is happening. So what is happening here? What is happening here? Let's see. So for this guy to exist as plus 3, it means that it lost 3 electrons. That's what it means. That's how it exists as plus 3. It lost 3 electrons. For this guy to exist as minus 1, it means that it gained 1 electron. Okay, so we know that this guy gained the electron and this guy lost the electron. Remember, we said the one that lost the electron is undergoing oxidation. So gallium undergoes oxidation, oxidation, and this is going to help us keep this information. Bromine undergoes reduction. Okay, so means that bromine gained the electrons, gained electron. So bromine undergoes reduction. Okay, and that's typical. Most bromine is an example of a halogen. The halogens, they need one extra electron to make their cell complete, so they are ready to gain. Remember what we said, the bromine is part of the group called halogen. They will readily gain electrons. So because gallium undergoes oxidation, gallium is also called the what? The reducing agent. It's called a reducing agent. It happily it happily gave away its electrons. It lost the electron, it reduced. So it happily gave away its electrons. So it was helping for bromine to undergo the reaction. So this is the reducing agent. And obviously this is also, so bromine becomes the oxidation or oxidizing agent because he is the one that removed the electrons from the other person. He gained the electrons, so he happily helped to remove the electrons from the other guy. So bromine is now the reducing agent. Gallium becomes, or gallium, or whatever you want to call it, becomes the reducing agent. So this helps us to solve our question. So this is the reductant. Reducing agent is the same as reductant. I hope you're paying attention. Oxidizing agent becomes the oxidant. Okay, oxidant, reductant, and oxidant. Okay, so keep them. So bromine is our oxidizing agent. So yeah, bromine is our oxidizing agent. Our gallium is gallium is our reducing agent. Great, great, great. So then that helps us to come to the conclusion of analyzing this reaction. So don't forget, to help us, we had to see whether any oxidation number or oxidation state changed. And we're able to confirm that gallium and bromine, they were just existing as zero, no charge. But when all of a sudden, when you go to the product side, we see that gallium had to have a charge of +3, bromine had to have a charge of -1, so that they combine to form gallium bromide. To form gallium bromide, that means that they underwent a change in the oxidation state. Gallium, which was 0, now increased to become +3, means it lost 3 electrons. Bromine, which was 0, decreased its oxidation state, now it becomes -1, means it gained electron. I hope you're following. And that's how we're able to conclude and know that, okay, this is a redox reaction. And we said that the one that lost the electrons, Thus, gallium became plus 3, means it lost 3 electrons. Gallium is the reducing is gallium undergoes oxidation. Bromine is the guy that gains electrons, is the negatively charged. Bromine undergoes reduction, and we are saying that based on this, the one that undergoes oxidation results in being the reducing agent, and the one that undergoes reduction becomes the what? The oxidizing agent. Don't forget, we said that most fuels normally are the what? The reductants. Yeah, most fuels are the reductants. Most fuels are the reductants. Okay, great, 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 great. So, any questions? Any questions? Any questions? Any questions? Okay, if there are no questions in your follow, you want to look at. So I'm gonna want you to look at this. So I'm gonna ask all of you. What do you think about this? Is this gonna be a redox reaction? I want you to try. Take your notebook right now. Look at this carefully. Do you think it's a redox reaction, and why? Do you think it's not a real redox reaction, and why? Your understanding is very important here. Great. So hopefully you've been able to Analyze this yourself. I don't know the answers you came by, okay? But we're going to do this together. We're going to look at this together. Okay, so let's look at this together. So let's look at H. So H, hydrogen hydrogen and oxygen. Hydrogen is zero here. Oxygen is also zero here, as you can see. Now let's look at the product side. On the product side, what are we seeing here? We're seeing hydrogen combining with oxygen to form water. The only way this is possible is that hydrogen has to have undergone a reaction here. So this particular one it's interesting. It's interesting because we're seeing hydrogen and oxygen, and we're seeing hydrogen oxygen. So we call this kind of reaction a disproportionation reaction because it involves the same element. Okay, it involves oxygen undergoing both. So in this particular type, we're going to see oxygen undergo oxidation, and now oxygen now is going to undergo reaction too. Okay, so we're going to see it. We're going to see it together. Okay, so to look at oxygen carefully, you're going to realize that we're going to see that oxygen here at the same time oxygen again here. So that's the unique thing here we're going to look at. Okay, great, great, great. Now to help us really understand this, we have to look carefully to know what is going on in this side of the reaction. So this is a compound. Okay, so before so our initial statement cannot be true. We can't say that it was just 0 0 because it's a compound. So let's look at it carefully. What was happening in this compound? Hydrogen had to combine with oxygen. Okay, so it means that, as you can see, there's two. As you can see, it had to there had to be there had to be a reaction or a combination here for hydrogen and oxygen to come together. Okay, now remember what we said about the rules in oxidation number when we're assigning oxidation number. Remember we said that there are instances where the oxidation number for certain elements are going to change. Okay, so we're going to go back right now. I want you to go see that before we come back here. Okay, so let's go back and go see it. Let's go back. We're going backwards to no, I'm sorry, I'm going forward. Let's go back. We're going to go back and read one rule because it's important here. We need that rule. Look at what we said here. We said that oxygen, the oxidation number for oxygen, everybody, let's look at this carefully. Most of the times is -2, but there's an exception. Sometimes it's going to be -1 in a compound called peroxide. So anytime oxygen exists as 0 2 O2 with -2. So when we have oxygen as a peroxide, its oxidation number is not going to be -2. Its oxidation number is going to be -1. Okay, so that's what we're seeing here. Keep that in mind. Okay, keep that in mind. That's very important. Keep that in mind. So let's go back. Let's go back. We're going to see what is happening here. Let's go back. We're going to see what is happening in our original. So let's go back here. We're going to see. Sorry, let me find. Great. So that's what is going to happen. So remember what I'm saying. I'm saying that this kind of reaction is a unique reaction. It's called a disproportionate reaction. Disproportionation reaction. Disproportionation reaction. What we are trying to say is that one element is undergoing two things. So the same oxygen is undergoing a reduction. At the same time, the oxygen is undergoing an oxidation. So that's why it's a disproportionation reaction, okay? And we are going to have to analyze it in that sense. Okay, so let's look at the oxygen undergoing all the two. So let's start. We are saying that in this reaction, hydrogen had to combine with oxygen, okay? So hydrogen had to combine with oxygen. The only way this could be possible. So this is an example. This is a peroxide. This is where oxygen is existing as. We said that always the oxygen's oxidation number is -2, but there are certain special instances where it's -1. One of those instances here, oxygen is existing as -1. Okay, so in this instance, oxygen is existing as -1. So oxygen is existing as -1 here. Let's look at what happens in this on this side. In this side of the equation, we see hydrogen and oxygen again. Look at this. That this time we're seeing that hydrogen is +1 here. That oxygen is still -2. That's the only way they ended up being H. The 2 goes to hydrogen. The 1 goes to oxygen. So this is where they were. Then it becomes H2O. So we see that oxygen was -1 here. But now it becomes -2. Okay. So it's -1 here. It becomes -2 in this particular instance. Okay. The oxidation number has changed. So that's why we know that this is a redox reaction. Okay. But the same oxygen too is undergoing something else. Look at what is happening here. This same oxygen, look at oxygen. We said it's -1 here. Now look at oxygen inside this reaction or in this particular situation. Oxygen is existing as 0. There's no charge. It's existing as oxygen in its elemental state. Oxygen in its elemental state is a gas, 0. So oxygen is the same oxygen is undergoing here where its oxidation number is changing. Oxidation number, it was -1 here. In this instance, it's -2. But that same oxygen again in this instance, it's reduced to 0. Okay, so this is a special situation. We call this a disproportionation reaction because it's disproportional. I mean, oxygen is either supposed to, one element is supposed to undergo reduction, the other element is supposed to undergo oxidation. In this situation, one element, oxygen, is undergoing reduction. At the same time, it's also undergoing oxidation. Okay, so that's what we want to take note of. The same oxygen is -1 here. In this situation, it's -2. There's it. The same oxygen in a different situation, it's -1 here, but now it becomes 0. So this is disproportionate. So that's why we call this a disproportionation reaction. Okay, so the same substance, oxygen, is functioning as the reductant. At the same time, it's functioning as the oxidant. So we call this a disproportionation reaction. The same oxygen undergoes oxidation where it loses electrons. It loses electrons. That same oxygen now is undergoing reduction where it's gaining electrons. Okay, so because it's -1 here, the only way it can become 0 here, it lost that 1 electron. Now that same oxygen is -2 here. The only way it's -2 is that it gained 1 more electron. So we see the same oxygen acting in 2 ways. It's acting as the oxidant, at the same time it's acting as a reductant. So we call this type a disproportionation reaction. So keep that in mind. When we have one element being the reductant, at the same time that element being the oxidant, we call that a disproportionation reaction. Okay, so keep that in mind. Please make sure you're writing something down. Pause this, go back again, go through it together. Take your time, go through this. It's necessary. Okay, that is why it's a video. I want to look at one more example, then you're going to try this yourself. So let's look at this. Let's look at this. So let's look at this carefully. Once again, do you think this is a redox reaction or not? What do you think? Is this a redox reaction or it's not a redox reaction? Remember, let's try this. If it's a redox reaction, the oxidation states are going to change. Once I can notice any oxidation states changing, then it means it's a redox reaction. If the oxidation state doesn't change, then it's not a redox reaction. So let's look at this together. For BaCl2 to be combined, it means that Ba was a separate entity, Cl was a separate entity. Ba was +2. That's the only way that these two went to chlorine. Chlorine is -1. They exchange, then we have Ba1Cl2, which becomes BaCl. See, the oxidation is +1, +2 here. This is -1. Let's come here. Look what is happening here. Ba is now combined with SO4. The only way they can be combined is that Ba was Ba here, SO4 was on its own here. Now SO4, its oxidation is -2, Ba is +2, so that we have them exchanging their charges. So Ba has the 2 from SO4, SO4 has the 2 from Ba, which is barium. Sorry, the 2 goes down here. So we have something like this with 2 here. These 2 cancels these 2, and that's how we had BaSO4. What do you see here? Ba is +2 here, Ba is still +2 here. So the oxidation state for barium doesn't change. See what is happening here? Chlorine is minus. Now let's look at chlorine here. We have KCl. The only way we have KCl combined as a compound is K was on its own, chlorine was on its own. Chlorine is -1, so K will have a charge of +1. They exchange their numbers, so K has 1 here, Cl has 1 from the K. 1 and 1, you don't write it, so you end up with KCl. As you can see, so look here, K has a oxidation number +1, chlorine has -1. So as you can see, chlorine is -1, chlorine is still -1. So far, barium is not changing oxidation, chlorine is also not changing. The only thing we need to now remember, SO4 is -2 here. You see, Let's check SO4 man here. If we check SO4 here and it's still -2, then we can conclude that this is not a reduction reaction. So let's see. K was combined with SO4. Remember we said K was +1. SO4 is here. Now, SO4, the oxidation number is -2, or the charge is -2 because it's an ion there. The charge for the ion, the whole anion is -2. The only way these two came here is this was +1. Then now they're going to combine, they exchange their numbers. Then we have K2SO4. Then this is minus, this is 1. We don't write the 1, so we're going to have K2SO4. Great. So that means K was still +1. So K is +1 here. K is still +1 here. Nothing has changed. SO4 is -2 here. SO4 is still -2 here, as you can see. So no change. There's no change. So there's no change. Let me write this well. There's no change in their oxidation numbers. So as we all just witnessed, oh no, what did I just do? Good. So there's no change. There's no change in their oxidation state. So there's no change in the oxidation state or oxidation number. No change in oxidation numbers so there's no change in the oxidation numbers. So we can conclude that it's not a redox reaction. Okay, great. So this is not redox reaction. Great. So this is not a redox reaction because there's no change as we just saw. Any questions? Any questions? Any questions? Any questions? Any questions? If you have any questions, please let me know. Any questions? Great. So I would like you to go try this for yourself. This is your exit ticket. I want you to try this for yourself. What do you think this will be? Try this in your notebook. Try this for yourself. And you can try this too. So try this too for yourself as we end today's class. Try this too, this one in your notebook, and try this too in your notebook. Okay? Try this in your notebook. We're going to continue. Try this in your notebook. I want you to try these two in your notebook. Okay? Try these two in your notebook. And as I said, try. Take a picture of whatever you try and send it to me. I don't need you to have it right or wrong. I just want you to try it. Okay? Try it. I'm going to give you a participation grade for trying it. So that's how I know you looked at this video. So try it and send it to me. There's going to be an option for you to send it to me. So try it and send it to me. Okay, for a participation grade. Great, great, great. So take care. Hopefully, I see you soon. If you are not writing notes, please go back, watch the video, take your time, practice together, and write some notes. So take care, okay?